Okay, so we're going to start with just looking at the graph of an exponential expression or function and its inverse. I guess sort of just as a precursor to all of this, I will say that some people believe that logarithms are the hardest part of this class. And I think that the reason that they seem challenging is because it's something we haven't done before. Like, you know, like when we study radical expressions, like it's a little bit new because there's variables or whatever, but we've taken the square root of a number before. And like when we study rational expressions, like there's polynomials and variables going on, but we've worked with fractions before. So like logarithms are sort of the first thing where like we haven't seen them at all. I mean, unless you saw them in a different class. It's not something that we did as kids with numbers before doing it with algebra in this class. So they're, you know, like a brand new thing, which is cool. We can do this. The key I have to emphasize for tonight's homework is that when you work with logarithms numerically, you can plug them into your calculator and they will spit out an answer and it will be right. And you can write it down, you'll get credit for it and I'll never know. However, the reason that we work with them numerically first is so that you can manipulate them and use the definition and like using concrete examples so that when we do it with variables tomorrow, you've already practiced with really concrete examples. If you use your calculator to evaluate the numerical ones, you're just kind of cheating yourself out of the understanding that you get from doing the manipulation that you will be able to use with variables. So like, even though it seems way easier to just plug it into your calculator, in the long run, you're not really doing yourself any good by depriving yourself the opportunity to mess around with logarithms. Plus, they're fun. They're like puzzles. Okay. So let's start with a couple graphs. So we're going to look at f of x equals, we'll do 2 to the x, and we're just going to graph it real quick. So I feel like we've done this one before. 0.25, 0.5, 1, 2, 4, 8. So 2 to the x. Remember that we have a horizontal asymptote on exponential functions because it's impossible to get a negative output if we have a positive number raised to any power. And so we're going to have negative 2.25, negative 1.5, 0, 1, 1, 2, 2, 4, and then 3, 8. So it ends up kind of coming along like this. And then it starts getting bigger and bigger and bigger and bigger and bigger, like so. Yeah, you guys remember this? So now we're going to graph its inverse. So we're going to graph f inverse of x. And remember that the outputs of f are the inputs of f inverse. So the inputs we're going to use are 0.25, 0.5, 1, 2, 4, 8. And the inputs of f are the outputs of f inverse, right? So essentially, on the graph of inverses, we're just swapping the x and y values. So negative 2, negative 1, 0, 1, 2, 3. So we've got 0.25, negative 2, 0.5, negative 1, 1, 0, 2, 1, 4, 2, and then 8, 3. Do you think I have an asymptote here? So remember over here we had a horizontal asymptote at y equals 0. Would it make sense for me to have an asymptote on the inverse? So if we think about the fact that the points swap our x and y values, If you think about that same idea with the asymptote, we're kind of swapping x and y. So we have a vertical asymptote at x equals 0. And you can sort of see it like, I mean, I could plug in like 20 more points, but you can sort of see it as it comes closer and closer, like to the left here, that it's going to get really, really close to that y-axis, but it's not actually going to touch it. Because remember that the x values of the inverse are the y values of the function. And if my y values never go below 0 for f, then that means my x values are never going to go below 0 for f inverse, because we're just swapping those x's and y's. So my inverse ends up looking like this. So we get infinitely close to that asymptote, but we don't ever touch it. Let's talk domain and range. What's the domain of 2 to the x? Yeah, right, we have an arrow going left, we have an arrow going right, and even though that gets really steep, it's not ever going to be vertical. And we don't have the way that I know I don't have a vertical asymptote on that black curve is because thinking about what my x values are, I can plug anything into the exponent of that expression, right? There's no exponent that I can't raise 2 to. And so my x value can be anything, even though it sort of looks like it. I don't know what word to use. Looks like it has like an asymptote because it gets really, really steep right there. It doesn't. So negative infinity to infinity.
And this is just pertaining to the first.
Yep, this is just the graph of f. So just that black curve. And then what about the range? What is the range of my function, f of x? Yeah, perfect. So that black curve never goes below the y or the x-axis, and so I don't have any negative y values. And then it never touches the x-axis either, so it's not equal to 0. So it is 0 to infinity, and not including 0. So then, looking at the domain and range of my inverse, the domain is what? For the blue one, look at x values.
Would that be the inverse of the range?
Yeah, so exactly. The domain of my inverse is just the range of my function. So it's 0 to infinity. And we can see that on the graph as well, right, that we're getting infinitely close to the y-axis, but we'll never touch it. So there is no blue to the left of the y-axis. There's no negative x values. And then I have an arrow going right, so it's going to go all the way. So then what's the range of my inverse?
Negative infinity, positive.
Mm-hmm. It's a little harder to see that on this graph because it kind of levels off. But remember that the range of my inverse is the domain of the function, right? So if the domain is negative infinity to infinity, then the range of the inverse has to be negative infinity to infinity. So again, even though it sort of looks like it levels off, it's going to keep increasing just really slowly. It doesn't actually have an upper bound, so a value that it doesn't get past.
So that's how the domain and ranges are on like those and all of those.
Uh-huh.
Okay.
Yeah, and so I can even generalize this. So forget the 2. Let's call this a to the x. And I'm not going to be able to do as many points, but the 2 main points that we typically graph when we're graphing these are 0, 1, because anything to the 0 power is 1, and then 1a. And we did that the other day when we did the graph, right? because a to the first is just itself. And then we can do a couple points on our inverse. So 1, 0. So the graph will always have a x-intercept at 1, 0, and then a 1. So just flip-flopping those x's and y's. So this inverse right here, the inverse of an exponential function, is what we call the logarithm. This is log base a, that a is a subscript of x. That x is not an exponent. So it's log base a of x. It's not a raised to the x power or anything like that. I'll get lined. I'm going to do lined from now on so that we can get all the placement right. Some of these things can like start jumping all over the place in people's homework, so we'll just work on that. And the one thing I want you to take away from this, I mean, other than the general shape of the graphs, because so a good question on a test per se may be like if I were to say like here's the graph of, or I might not even give you the graph, be like, okay, graph f of x equals 5 to the x and its inverse, right? And so whenever you're asked to graph an inverse, just graph the original function and then swap the x's and y's. That's easier than being like, okay, I have to figure out what the inverse is and then graph that separately. Like, if you can come up with the graph of the original function, like a nice little table like we did, and then just swap your x values and y values, that'll give you the graph of the inverse. And that's probably the easiest way to graph those inverses. But the other thing you want to take from this is the domain. The domain of all logarithm functions of log base anything is 0 to infinity. So remember how when we first started doing domains, we said, okay, we just have two restrictions for now. There's a restriction when we divide because we can't divide by 0. And there's a restriction when we take even roots because you can't take the even root of a negative. Well, now we have another operation that has a restriction. So when you're trying to find the domain of any logarithm function, whatever your input is, so whatever you're taking the logarithm of, has to be greater than 0. So if I wanted like to find the domain of f of x equals log base 4, and we are going to define logarithm in much more detail here in a minute, so don't worry too much about that for now, of like x minus 6. So whatever you're taking the logarithm of, which in this case is x minus 6, has to be greater than 0. So it's a lot like finding the domain of a square root function. The big difference is that it's strictly greater than 0. It is not greater than or equal to 0. You can't plug 0 into a logarithm because there's no exponent. You can raise anything to get 0. So we say x minus 6 is strictly greater than 0, which means that x is greater than 6. So my domain is 6 to infinity. So it is a lot like all the domains we've found already. This is just another operation that has a restriction. Does that make sense? Okay, so now let's get into like what the logarithm really is. So one thing to keep in mind about the logarithm is that its entire definition is just based on the fact that it is the inverse of the exponential function. So much like the square root, like the square root's kind of defined in terms of squaring something, right? It's like the square root of a number is whatever you have to square to get it, right? So it's all defined based on what it undoes or what it is the inverse of, and the logarithm is the same thing. So we always have to kind of think of it with respect to the exponential function that it's the inverse of, because that's really the only way it's defined. So let's write a definition. Maybe. There we go. So let A be a positive number. Which is not equal to 1. And the reason it can't be equal to 1 is, like, if we go back to this guy, that A is the base of the exponential function that the logarithm is the inverse of. If that exponential function was 1 to the x, would it be an exponential function? I mean, like, what is 1 to any power? It's just 1, right? So it wouldn't be an exponential function. It would be a constant function. So that's why we say that A can't be 1, because then we're not actually working with an exponential function. We're just like, we have a straight line. Boring. Okay. So let A be a positive number, which is not equal to 1. Then we say the logarithm base A of x is the exponent to which we raise A in order to get x. Everything we do with logarithms is based on this definition. If you understand the definition of a logarithm, you can pretty much do anything with them, because we have all these great, like, exponent rules. And if you remember that the logarithm is an exponent, right? It says the logarithm is the exponent to which we raise A in order to get x. So a logarithm is an exponent, which means that all our exponent rules tell us how to manipulate logarithms, because they are exponents. If you can understand the definition, everything we do with logarithms follows from it, and then you don't have to try to remember all these little tiny rules about logarithms, because they all just come from the definition. So let's write it symbolically. So symbolically, we are saying log. So the logarithm base A, again, that A is a subscript. I feel like I should put it lower. Of x is equal to y if and only if your base raised to the y power gives you x. So the logarithm base A of x is equal to the exponent that you raise A in order to get x. As far as switching back and forth between these equations, so from a logarithmic equation to an exponential equation, I always just remember the logarithm is equal to the exponent, always. The bases are all the same, so the base of a logarithm is the same as the base of the exponential expression that corresponds to it, and then the logarithm is always equal to the exponent. Logarithm is an exponent. So, oh, and then this is how we say this. We read this log base A of x. And this is another one of those times, guys, I know you roll your eyes at me when I say things like this, but saying it correctly isn't just like me being like, oh, you should talk like a mathematician. It's like, if you often saying things incorrectly makes you perceive them incorrectly. Like, a lot of people will be like, log of A to the x. which makes it sound a whole lot like you're taking the logarithm of a raised to the x power, which isn't what this is. It's log base a, so the base of the logarithm is a, and the thing we're taking the logarithm of is x. So saying it correctly helps us understand exactly what it is that what the expression is. I promise I'm not just being super picky about it. So let's do a couple examples so we can work with this a little bit. So let's do this guy first. We're going to evaluate log base 2 of 8. And you don't need parentheses unless there's like addition or subtraction in there, but I found that like that's another way to help prevent trying to make that an exponent. Like people really want like that 8 to be an exponent for some reason. Like it just like sometimes scoots up into an exponent. So I think that the parentheses help with that to keep it on that same line and not think of it as 2 to the 8th power. So if I want to find log base 2 of 8, I ask myself the question, to what exponent, oops, that's not how you spell exponent, exponent must I raise 2 in order to get 8? Or you can ask 2 to what power is 8? So it's just like when we do like square roots. We're like, what number do I have to square to get such and such? So 2 to what power is 8? 3. And so log base 2 of 8 is equal to 3. It is equal to the exponent I have to raise my base to in order to get 8. I strongly recommend that you write those 2 sentences or questions in your notes to help you remember, because those are really the key. Like, to evaluating these things is just asking yourself that question. Okay, so 5 to what power is 1 over 25? So that's not maybe like immediately obvious, but one good way to approach these is to try to write this as an exponential expression with a base of 5. Like if it was just 25, we could write it as 5 to the 2nd power, right? So this is the same as log base 5 of 1 over 5 squared. Yeah, very good. So which is the same as log base 5 of 5 to the negative 2. So now, to what exponent must I raise 5 to get 5 to the negative 2? Negative 2, right? Don't overthink. You get 5 to the negative 2 by raising 5 to the negative 2 power, right? So the logarithm is the exponent that I raise 5 to in order to get 5 to the negative 2. So if you can't, like when we did log base 2 of 8, we could sort of just think it through. If you can't come up with the answer to the question, like just off the top of your head, then try rewriting the input as an exponential expression with the base of the logarithm, like we did here. We wrote 1/25 as 5 raised to some power. so let's talk a little bit more about the relationship between exponential functions and logarithmic functions. So, the logarithm base A is the inverse of the exponential function with base A. So symbolically, we're saying if f of x is equal to a to the x, so the exponential function with base A, then f inverse of x is equal to log base A of x. When did it stop recording? That's really annoying. Okay. The common logarithm is base 10. And we don't write the base. So this is sort of like the square root. We don't write the index of 2 on the square root because it's the most common one. The same is true here. When we write base 10 logarithm, the base 10 logarithm, we just write log. So the base. So f of x equals log of x is log base 10 of x. So whenever you see a logarithm without a base written, so just the word log, then it is implied that that's the common log, so base 10. And then the other one is the natural logarithm. Is base E. So E is Euler's number. It's an irrational number, a decimal that goes on forever and never repeats, right? So we just call it E so that we can write it in its exact form. And we talked the other day a little bit about E, right?
Yeah.
And so we'll use that for continuous exponential functions. We'll see it quite a bit. So the natural logarithm is the base E logarithm, and it has a special notation. It is written ln of x. So that's an L, not an I or a 1. So f of x equals ln of x, the natural log of x.
Why do you not put x in parentheses?
I don't know, because I didn't. You don't technically need the parentheses unless there's like addition or subtraction in the input, but it's a good habit to get into. Okay, so let's do some examples before we gotta go. We're going to rewrite in as a logarithmic equation. So we'll just do a bunch of them. So let's start with 16 equals 2 to the x. So when we say rewrite as a logarithmic equation, we're just saying like take this exponential equation and use the definition of the logarithm to rewrite it in logarithmic form. So like going back to our definition right here, we're just switching back and forth between those two equations, which are equivalent to one another. So the base is easy to figure out because it's just the base, right? So the base of this exponential expression is 2. So I have log base 2, and then remember, so the key to writing these is that the logarithm is the exponent. So the logarithm is equal to the exponent. So equals x, and then there's only one place for the 16 to go. So log base 2 of 16 is equal to the exponent we raised 2 to in order to get 16. If you just remember that the logarithm is equal to the exponent, that makes these so much easier. You're not evaluating anything here. We're just rewriting. So let's do 10 to the negative third equals 0.001. So what's my base? My base is 10. The base of the exponential expression is the base of the logarithm. So my base is 10, which means I don't write the base. It's the common log of what? What am I taking the log of? 0.001 equals negative 3. You don't have to write it in order. If remembering that the logarithm is equal to the exponent helps you, write equals negative 3 first, and then be like, oh, there's only one place left for me to put that 0.001.
So why don't you put base 10?
Because the common log, we don't write the base. Just like with the square root, we don't write the 2 as the index. It's just because it's the most common one. Let's go the other direction. So let's do the natural log of p equals 8. So what's the base of my exponential expression going to be? So the natural log is base e. Right? And that's just from the definition of the natural log. And then remember that the logarithm is equal to the exponent, so I'm going to write e to the 8. And then there's only one place left for the p to go. Gosh, it's such a bummer we have to leave. I could do this all day. It's so much fun. Okay. Log base 2 of 32 is equal to 5. So if I want to write that as an exponential expression, my base is the base of the logarithm and the base of the exponential expression are the same. 2, yes. And then what's my exponent? 5, because the logarithm is equal to the exponent every single time. And then that 32 is the only number left. Good. So we've gone over, so tonight you just have 9.4 in my math lab. You have no written. You will have problems like this, and then you'll have some, like these examples that we did at the beginning where you evaluate. Again, using your calculator is just going to prevent you from actually working through these and learning and getting more comfortable with how they work. And guys, I know I say it every day,